So shall we start now? Am I audible? Can anyone confirm by unmuting yourself and speak? Hello? Okay, thank you, Mohit. And is also my screen visible? Okay, cool. Okay. So this video would be recorded, um, and let I wish this session can be interactive as much as possible. Whatever doubts you have, just feel free to um, shout out and just unmute yourself and ask or post it in the chat message. Um, I'll try to answer all of those doubts within this 1 hour session as much as possible. So the how the sessions would work is that from this week onwards, every week at the same time, I would be conducting these live sessions. And what I will be doing is I will be discussing around 10 questions or 10 to 15 questions of the previous offering of the same operating systems NPTEL course. Okay. So, by the way, sorry, I should introduce myself. I'm Sai Venkatakrishnan, a PhD scholar in Indian Institute of Technology, Madras, in the Department of Computer Science and Engineering. So, this live session is for the course Operating Systems Fundamentals. Okay. So, the agenda would be as we'll be discussing questions which were posted in the previous offering of the same course, that is last year 2021, and I'll be going through how to approach the question, the MCQ questions, or the solutions, etc. So if you have any doubts with respect to those questions or anything in the lecture also, you can unmute yourself or send it in the chat message. Okay. So make use of these live sessions, it's for your benefit only. Okay. So I'll start the session. So the first question is what's the objective of an operating system? There are four options that are given. The first option is making the hardware usage more efficient. Second is making the system more easier to use. The third is it's easier to solve user problems. And the fourth option is all of the above. Can anyone try to tell what the answer is for the first question? Okay. Yeah. So the answer is option D. The reason being, what what does an operating system actually do? The operating system is nothing but if you have the user application, and this is the hardware over here. And how can the application interact with the hardware? In between, there comes this operating system layer. And this operating system is a way of abstraction so that it gives out some API, those system calls, and all those things that this application can directly ask. So, say if I have one hardware, if I have this application, I want to run it on two hardware systems. I have the source code. I can just, if it's running on the same OS, then it should be mostly be compatible with the other hardware also. Say if this is some x86 hardware and if this is like ARM hardware, the ARM ISA and those things. If I want to run the same application on both x86 as well as ARM, and both are running Linux OS, we should recompile the application, but the underlying difficulties, that is the system calls, those exact configuration, those things all the application need not worry. It can just leave it to the operating system and make use of the standard system calls to run on the hardware. And also the other thing with the operating system is it allows you to do multiple tasks. So if you have the same if you have say multiple applications running on the hardware, then how to share the resources between those applications and all those things. The operating system acts as a moderator. So this is application 1 and this is application 2, and you have the OS sitting over here, and this is your hardware which has the main memory and access to the uh, this is the memory. Let's assume this as the memory and other IO device. So in that case, when both the applications try to access the IO interface, say like scanf or printf, in that case, which application should get access first? All those things we can leave it to the OS, and assume that the OS is doing a good job of scheduling how these applications and how they access the IO devices, all those hardware devices. So D is the correct option. Any doubts till now? Any clarifications? Yeah, if not, I'll move to the second question. Okay, let me just move on. So question 2. Okay. Question 2 is one routine in an interrupt service. The interrupt service routine, how many interrupts can it handle? Can anyone try answering this question? How many interrupts can the interrupt service routine handle, the ISR? Just any guess or something? So let me just say this is your operating system running, and you are running an application over here, A1, and suddenly some interrupt from the hardware layer, it raises an interrupt. So in that case, what happens is there would be a predetermined location, the code location, which should be invoked whenever an interrupt is raised. And at that code location, there would be this ISR, the interrupt service routine. The question is, this interrupt service routine, how many interrupts can it handle at a time? Say when this ISR is being, say one interrupt is being raised and it enters into the ISR, the interrupt service routine, and that interrupt is being handled. If another interrupt is raised, what would happen? Whether the same interrupt service routine can handle multiple interrupts at the same time or not. So that's the question. Can anyone just guess an answer? Let's see whether it's right or wrong. Just a wild guess, like whether it's just one interrupt or any number of interrupts can it handle. Okay, so Mohit tells a one interrupt. Okay, so let's see why the yeah, one interrupt. So the correct answer is one interrupt. Yes, you have got it right. So let's see why. What's the importance of the interrupt service routine? The thing is, these interrupt service routines actually should are invoked whenever this hardware layer raises the interrupt. So in that case, what the ISR, the steps what the ISR should follow is, one, it should save and save all the registers which are being the register values. It should save it in some memory location. And the second is, it should save all the context, all the registers and all those things, and then it should properly handle that interrupt. So by handling the interrupt, what it means is there can be like many types of interrupts. Say an IO device is being asking for some memory location or something, or some other external device such as like a USB, which whatever you plugged into your laptop, it is asking for some access to a specific memory location or something like that. So in that case, it would raise an interrupt or interrupt and would request the OS to service that interrupt. So there are many types of interrupt. So in that case, what the operating system should do is it should invoke this interrupt service routine with respect to that particular interrupt and do first this first step, saving the registers and all the context, save it into a secure memory so that once this interrupt is handled, whatever task the operating system was continuing, it should continue from that same point. Say the operating system was executing some program, and in between this interrupt was being raised. What it should do is by saving these registers and all those things, it it makes sure that once this interrupt is being serviced, once the interrupt request is handled, it can safely come back and restore the execution and start from the point where it left and continue execution. So that's the importance of this first step, saving the context and saving the registers and all the context. And once that is saved, it can very well handle the interrupts, whatever the logic is being included within the interrupt, it can do. And the thing is, usually these interrupt service routines should be serialized. As in, say, like you have say if multiple interrupts are being raised by the hardware, then the OS has to service these interrupts one at a time only, because the first step, saving the context and saving the registers, has to be serialized. As in, it cannot do it like simultaneously. It cannot save handle all these interrupts. So there is the limitation that the interrupt service routine can handle only one interrupt at a time, mainly because of this saving the context switch and all these things. Once this is done, um, again, while handling the interrupt logic when it is getting executed as part of the ISR, any other interrupt if it comes, then it can be serviced. So, an interesting thing for you to go and look into is preemptive kernel and non-preemptive kernel. I guess it will be taught in the next uh, in a couple of lectures. I think this would be touched upon, non-preemptive kernels. So what this mainly deals with is, say the OS is handling one interrupt and another interrupt comes, it's being raised. What should I do? Should I first finish handling this interrupt and then go to that interrupt and handle the second interrupt, or should I just stop this interrupt itself, the first interrupt, whatever I'm handling, I should stop it, save the context, and service that second interrupt, and then return back to the first interrupt. So all these logics are all being implemented in the kernel. So if it stops in between and handles the second interrupt, so it's giving priority to the second interrupt to service that particular interrupt. Say in a, if you are going in a automobile, if you are going in a car, so in that case, say one interrupt is your MP4 player trying to access the audio message, sorry, the audio files and play the sound. So that is interrupt one. And say the second interrupt is the automatic braking application, which is for the say it detects some object crossing the car in between, and it raises an interrupt saying that the brake should be applied immediately. So which one should the OS give priority to? Say if this interrupt one was raised first and this is the second interrupt, if since this braking thing is more important, the operating system should give priority to this second interrupt and service this first, and then go on and handle the first interrupt, which is just handling the audio files. So all these logics can be encoded into the kernel, and based on the scenario in which these operating systems are used, say whether it's in an automobile system where these priority things have to be taken into consideration depending on the type of the interrupt, all these things, the way the interrupts are handled would be different. But the general notion is whenever the interrupt is being handled, at least the first few steps, it should be serialized. Serialized in the sense only that interrupt has to be active. The following steps, if it's say in a multi-core system or something, it can be handled simultaneously. But those depend, like those are all like advanced concepts. But at a time there is this limitation that only one road interrupt can be handled, at least for some period of time, the initial period when the registers are being saved into memory and all those things. Okay. Any questions till now? In this interrupt service routine and all those things? Okay. In that case, I will move to the third question. Feel free to unmute or and shoot up your question. Okay. So the third question is, during an interrupt, control is transferred. During an interrupt, what happens? That's the question. Option A is the control is transferred to the interrupt service routine. Option B is the interrupt architecture saves the address of the interrupted instruction. Option C is the operating system preserves the state of the CPU. And option D, all of the above. So any guess which one is the correct option? A, B, C, or D? D. Okay. Yeah. Yeah. D is the correct option. Can any one of you just unmute yourself and tell why D is the correct option? Okay, let me just continue in the want of time. So the the reason why D is the correct option is what happens during an interrupt, as we had seen before. First, the control is transferred to the interrupt service routine. So if you had seen the video lectures, whenever the interrupt is being raised from the hardware, it looks into something called as the interrupt vector, the interrupt vector table. So based on the type of the interrupt, each interrupt will have an ID associated with it. So based on this ID, it will index into this interrupt vector table. Interrupt vector is just like an array of addresses which will point to the code location where the interrupt service routines would be stored. So based on this ID, it will index into the interrupt vector, and in the interrupt vector, once it starts in the interrupt service routine, it will preserve the state of the CPU, as in it will save the CPU registers and all those specific registers. So the reason why the state of the CPU, the registers and all those things has to be saved in memory is that, if you recall, the registers are volatile in nature. Okay, and also the registers would be reused, and those register values would be populated and corrupted when the interrupt service routine executes, because it's the same set of say in x86 ISA, there are just around like 16 to 32 registers. So the same registers only would be reused when the interrupt service routine logic is being executed. So to assure that the once the interrupt is handled, if I have to return back to the same instruction at which point this interrupt was raised, then the register values, everything should be stored in memory, and before returning back to the interrupted instruction, I should restore back all these registers Restore as in I should load back all the values from that stored memory into these registers and resume execution. So all these steps occur during an interrupt and all these are required. So that's why answer D, all of the above. Okay. So any doubts? If not, I'll just move ahead with the fourth question. Okay. So the fourth question is as follows. On facing an interrupt, the transfer of control to interrupt service routine is made through what? Is it system processes or is it the bootstrap program? Is it the interrupt vector or is it the interrupt kernel? Any thoughts? Any guesses on whether it would be option A, B, C, or D? Option C. Mohit tells option C. Okay. Anyone else want to take a chance? Okay, Akash also option C. Okay. Okay. Let us see like what each option is and let us go through it. So one is system processes. So system process is nothing but just the OS processes and all those things. So what we have learned till now is when the hardware is there and this is the hardware and this is the OS. When interrupt is raised, the first point of thing is goes to the ISR, and how it goes to the ISR, the control is transferred to the ISR. Is we mention it's through the interrupt vector. Okay, so that's why option C. Why not option B? Is this the bootstrap program is nothing but the first program that would be um, executed whenever the thing is reset, the on power on. So this bootstrap program is nothing but it loads the operating system and all those things. So that's what the bootstrap program does. Interrupt kernel is nothing but just a made up term. It does not mean anything. Okay, so just for to confuse, that's all. And option A, system processes as such does not do anything with respect to handling the interrupts. Whenever this interrupt is being raised, automatically based on the interrupt vector, it looks into this table, it reads the ISR code location, the ISR PC value, the program counter value, and automatically the execution starts from that particular PC value. So interrupt vector is the most important key, the table which is being used to find out where this ISR is located in memory and continue execution to handle that interrupt. Okay. Um, let's move to the fifth question. So which of the following memory storage is mostly volatile in nature? Any idea? Option A, main memory. Option B, secondary memory. Option C, tertiary memory. D, none of the above. So which of the following is volatile? So by volatile is, say if you power off the system or something, it gets erased automatically. Okay, Akash tells option A. Okay, RAM. So everyone are telling option A. So this main memory, yes, as everyone mentioned, it's option A, main memory is the volatile. So if you recall what you have seen in the video lectures, there is this memory hierarchy. So at one thing, what are the various characteristics that a memory device would usually have? So one is whether it's volatile or not. The second is whether it's speed of the speed of the memory access, how fast it accesses the memory, and cost cost per say byte. So to store 1 byte of information in that memory device, what's the cost. So these are the three main features based on which these memory devices are classified. So whenever the um, um, you execute the programs, all those things, the first level of memory that is being used would be your registers. So all those R1, say R16, 16 registers are there. These are the fastest memory slots that is present on your chip itself. So by on the chip is there won't be any delay in accessing these registers. Since it's present on the chip, there you won't have any external bus or something that is used to access these registers, and it's part of the pipeline itself. In the hardware, these registers should be there, and the connection should be hardwired also. So this is the first level of registers, the first level of memory, which is the fastest. It's volatile, but and also the number of registers, you can argue like, okay, like I have 16, why can't I increase it more? But remember that all these registers have to be on the chip. So if you keep on placing these registers on the chip, the size of the chip would increase, and also if the size increases, then the power required to run the chip, the temperature and all those things will come into picture. And those are like few limitations. So that's why the number of registers present on your chip is limited. So not all the information that an application accesses can be present always in the register. So for that we go to the next level of memory, which is your RAM, that is main memory. So this is also volatile, and it is based on this DRAM, the DRAM technology and those things. And the speed is not as fast as these registers, but it is quite fast. Okay, and it's just like a trade-off whether you want the cost to be more. So if the cost is more, the speed is also more, but your DRAM should be huge enough so that the application, whatever memory it actively uses, say you are using a gaming application, or you are doing some video editing. So in that case, the memory that is being used actively, say within a minute or so, would be so huge. Say it will be like around 10 GB or something. Your RAM should hold that much of content for smooth operation. If not, what happens? It will be swapped to the disk and all those things. So initially, in the when the systems were in the when you see the evolution of systems, initially these were there were these disks actually, the main the optical disks and all those things, the tape devices, all those things. But the thing with the tape devices is that the it is permanent in nature, it is non-volatile. Okay, it's non-volatile, but the speed is very low. The cost is very low, but the speed is very low. So once this processor speed began to increase due to the Samdol's law and all those things, the number of transistors and the processor speed increased, the latency to access the tape memory and get all the uh, data for the hardware to run upon that data became too slow. So for that, what they did, they added these registers in between, they added the RAM in between, so to improve the memory latency, so that if the most used 16 words will be present in the registers, the next mostly used, the 10 GB, say your RAM is 10 GB, then that mostly used memory would be present, values should be present in your RAM, and the remaining memory can be the values can be present in the tape, which is non-volatile in nature. So even if it gets like power off or something, the tape would, it, the value should be retained as such. But for the working model and all those things, it's the RAM and the registers that would be actively used. So this tape and those things, actually the hard disk drives, the magnetic disk drives are what is the secondary memory. Tertiary memory is something like optical discs and all those things, where you generally you don't use it in a day-to-day life, but you just use it, say like a weekly backup or something like that. Whenever you have so much of information in a industrial setting, you have to back up the information regularly, or at those times you do this tertiary memory. That's what is usually termed as tertiary memory, and those can be accessed at times whenever, say, your server gets corrupted or something, that actual secondary memory gets corrupted. You can access this tertiary memory temporarily and use the data present in that tertiary memory to service your requests and all those things. Okay, so the question is mostly volatile in nature, and that's the main memory, and it's also the fastest among all these three. Okay, any questions till now? Okay, if not, we can move to the sixth question. Okay, so computer storage measurements are usually done in dash, and networking measurements are usually done in dash. So whether it's like bits, bytes, bytes and bits, bytes, bytes, or word bytes. So this is a question taken from the video lectures. If you had gone through, the professor would have mentioned what measurement, the unit of measurement would be preferred when we refer to computer storage and when we refer to networking. Any guesses? The least unit of measurement. Okay, someone tells B. Okay, okay, yes. So the thing is, usually this, if you see even in your day-to-day SIM card, those measurements and the online speed in network measurements, it usually in like Gbps, it's the small b over here, that is like bits per second. So networking measurements are usually done in bits per second. Okay. And computer storage, it is becoming quite cheap nowadays. If you just go and try to purchase a hard disk of say 2 TB or 1 TB, it's easily affordable compared to earlier days when the storage was costly. So in the storage nowadays, it's usually in terabytes or gigabytes. That's becoming the trend nowadays. So the unit of measurement for computer storage, the least unit is bytes, and for networking it is bits. And another reason for the least unit that can be expressed for this computer storage, that is being bytes, is the reason, it's because um, you see how your hardware is being designed. In your hardware, you have the registers, R1, R2, R3, all those return address register, the stack pointer register, all those registers are there. So as I mentioned previously, this register is the fastest memory slots present on chip, and these are limited in count. These are limited, and followed by that we have the RAM. So if you notice, what would the size of these registers be? Usually it would be the in the size of, say, like if you are in x86 64 Intel machines, the latest Intel those things, it would be like 64-bit registers. So 64-bit in the sense, whenever there is a load instruction, load R1 comma some memory address, some value present at this memory location A, how many bits or bytes would be loaded into this register at a time? So it would be 64 bits would be loaded. at a time. So the bus, which so this is the on-chip device. This is the chip, and if the on seeing this load instruction, it would access the main memory RAM, and it would load 64 bits, and this is usually termed as like a register word or a double word. So usually like word size, if someone tells if the word size is 64 bits, they tell like the number of words being transferred to all those things. It's usually 64 bits. It depends on the how many bits can be loaded into the register at a time when a load instruction executes. So that's the case. And since this is the smallest size of the value that can be stored in a register at a time, usually the storage measurements and all those things have also been adapted to this type of measurement, and that's the main another reason why it's like bytes actually and not bits, because bits does not make any sense in storage. It's just you will be the smallest say, if you are just handling one integer, it's also around 4 bytes in modern systems. So, and the character itself, if you want to do something meaningful, printing a character or something, it would be 1 byte actually. So this main reason that bytes is the smallest unit of measurement, whereas in networking measurements, it is costly, and also it's not free, so there is so much of congestion in networks and all those things, and that's the reason why it's always measured in bits. And also if you see, there is no like small set size of a packet or something based on the protocol. Say if you are using https or something, the size may differ, but it's always preferred to be described in bits to be flexible in nature. So that's the main reason. If there are any doubts, we can pause, or else I'll continue with the seventh question. So which of the following storage type is the fastest? Option A, optical disc or a magnetic tape. Option C, registers. Or option D, all of the above are equally fast. Any guesses? Which one is the fastest? Okay, registers. Okay, C. Yes, registers is the correct answer. Okay. So optical disc is a form of secondary device, and even magnetic tape is also sorry, this is tertiary, I guess tertiary or secondary. This is tertiary, and magnetic tape is a secondary device. These registers would be present on chip, and is the correct answer, registers. Okay, so this is a pretty straightforward question. I think we can move ahead to the eighth question. Okay, which provides a uniform interface between the controller and the kernel to manage the IO device, the input output device. So, so just yeah, okay. Mandip cells, B device drivers. Okay. Any other? Okay. Yes. B is the correct choice. Let's just let me just give a quick recap of what these device drivers are and why the device drivers are very important. So if you notice, there will be this hardware layer. Okay, the hardware will have, say you have a USB, you have a keyboard, you have a printer, something like that. So all this would be interfacing with your all those would be interfacing, and see this is the bus, and you have your CPU over here. So all these are interfacing in the bus. Now each one has its own functionality. it will have its own protocol, it will have its own registers, and it will have its own memory. Say this printer as such will have printer will have its own memory. It will have its own set of registers that it will be using, and it will have its own protocol of what to do and how to um, parse the information that is being given to the printer. Say whether it has to be printed in like landscape mode or A4 mode or something like that. All those things the printer has to decide, and for that it will be having some code within it and all those things, and that code would be stored in some memory location within the printer, and it will be accessing some registers which is local to the printer itself and all those things. Now when and in real world setting there can be many type of printers, many USB devices, and all these devices would be proprietary, as in say one would be manufactured by Samsung, one would be manufactured by Apple, and these two won't interface with each other. They would be using their own software, their own mechanisms to read the information and all those things, and they won't worry about compatibility. So in that case, how if I buy a new USB or a printer, if I want to use it with my system, how does the my CPU, my system, know how to send messages to the device, how to instruct the printer, okay, to print this document twice in a landscape mode, in a color setting, or in a black and white setting? How do I tell these instructions to the printer, given that it's like a each day I'm using a new printer or something like that? So how is this being achieved? So here comes the help of device drivers. So what these device drivers do is, these device drivers would be provided by the manufacturer itself. Say if Samsung is selling a printer, it will have its device, it will be selling a device driver also. It can be downloaded online. If Apple is selling something, or some manufacturer, say the SanDisk USB is selling something, its own device driver would be available online. Now what is being done is, the operating system would look at this device driver. When you download this device driver would usually be installed as in it will be kept as part of the operating system. And when the application wants to access any of these printers or anything, if it wants to say access this printer, it will invoke the API. So whatever this device driver has, or those API, it will make use, excuse me, it will make use of those APIs. It will enter into the kernel mode. It will make use of this uh, device driver that is being provided by the manufacturer to smoothly communicate via the bus to this external devices like printer or USB. So as a application developer, I need not worry about how to support these third party devices that are being connected to the system. I leave this functionality, this compatibility job, all these things to the manufacturer itself. The manufacturer has to provide these device drivers, and the advantage with these device drivers is it can be easily loaded into your operating system, and these device drivers will mostly run in the kernel mode. And these device drivers will be specific in nature, that is, it will know, okay, so say in this printer there are three registers like A1, A2, A3. It was named like these registers, and it is of size 8 bits only, like that, something like that. So those are all very specific to the printer. So what the device driver will do is, it will have that logic specifically as part of its functionality. And when it's loaded into the OS need not worry about what printer is being connected to the system and all these things. It just has to call the device driver and uh, pass on the instructions to the device driver, the high level instructions like printing in a black and white or something. The device driver has to pass that information in a format that this printer can understand, and this printer will have this controller. That's what is being meant by this controller over here in the question. This controller is nothing but the CPU attached to this printer, like a say like an 8086 chip or something like that, small chip that is not very powerful, but it will be efficient to do that task of printing again and again. So this device driver will interact with this CPU and perform the printing operation and all those things. So as an OS developer or as an application developer, I need not worry whether I'm using a Samsung printer or a Canon printer or anything. If the device driver is available, I can blindly install that and just interact with my printer, print documents, and if I'm not using it, I can uninstall the device driver. So uninstalling is I'm just deleting those files, those executables, and in that case I may not be able to access the printers. So this is how the device drivers and are used to interface between the controller and the kernel. And the key thing is it relieves a lot of effort used to make a variety of systems, variety of these devices to interact with your system. So by it's like a team effort. So the manufacturer, if he has these device drivers, okay, my printer is there, I have device drivers for Windows, Linux, and say Mac OS and all those things. For the manufacturer, it gives him an extra customer base. If by chance, if he says he does not have a device driver for the Mac OS, the Apple laptops, then anyone who is having an Apple laptop cannot access that printer, and in that case, they may not buy that printer also. So that's like a lost opportunity for him. So these device drivers are a way like to expand your customer base also in a case, and it's easy for the OS not to worry about the specifics of the system that is being the device that is being connected to the system. Okay. Any questions? If not, I'll move to the ninth question. Okay. Direct memory access transfers, the DMA transfer disks transfers the I/O data from the disk by what? With the help of the CPU by transferring a part of a data block at a time from buffer storage to memory, or option C, by generating one interrupt per data block to notify the device driver of the task completion, or none of the above. What's the any guesses what the correct choice would be? How the DMA access transfers the IO data, whether it always requires the CPU's help, or it just uh, generates like block by block from a buffer storage to memory like that, or it uses by generating an interrupt per data block to notify the completion, or is there some other mechanism that's not being specified in the option? Yes, the DMA uses the bus interface. Yes. So let me explain DMA thing. So you have the CPU, and this is the bus over here. You will have your DMA controller, and say this is your disk, and your this is your disk or main memory or whatever. Okay. So what happens is say, and this is your IO device or something like that. So what happens is, say if the IO device or something has to access some location in the disk or main memory. So usually DMA accesses in the main memory. So I will include this also. So this is your main memory, this thing. Okay, so say if my IO wants to access some address location at some address location A1 which is present in my main memory. So in that case, there are many ways to do this. The easy way is that it raises an interrupt. So it passes an interrupt, say I1, it raises an interrupt. The CPU looks at the interrupt, and what happens? It goes to the interrupt service routine, saves the context switch and everything, and it will access the location, the location A1, pass that data back via the bus to the IO device, gives back the data. So say this at a time, say the IO device, at a time it can issue, say like uh, it can receive 10 bytes of data, some like that load instruction is like that, let's assume. So in that case, if it wants to get some 100 bytes of data, and at a time it can ask the CPU for 10 bytes only or something, uh, and the CPU as such can only give 8 bytes or something like that, let's assume. Okay, so in that case, to get this total 100 bytes, each time what the IO should be doing, the IO devices, it will be raising an interrupt, then the ISR would be accessed, the saving the restoring the sorry, saving the register. So when an interrupt is being raised, there might be an application running in the user mode, so that application has to be stopped, it has to be it has to enter into the kernel mode, the saving the registers, all those things, then the ISR has to be handled, the ISR logic is executed, the interrupt is handled, that information, that whatever value is present in this A1 location, whatever is being asked by the IO device, has to be returned back. So for each 10 byte bit, right, 10 times the same, this total operation should be executing each time. So it should be like 10 interrupts, 10 times I'm saving the register, saving the registers, doing context switch from user to kernel mode, all those things are there. And if you remember, say usually this load operation, store operations should be very costly, as in it would take around like 100 cycles or something like that. It will take 100 cycles. And registers is not just one or two registers that you would be saving each time when an interrupt is raised. You should be storing all the registers. Say if there are 16 registers in x86, and also other registers like floating point registers in your x86 architecture, all these registers should be saved whenever the interrupt is being raised, and again it should be restored back. So all this would occur 10 times to just access this 100 bytes for the IO device. So this is usual, this is inefficient, and it leads to lots of performance delay. Say you're listening to an audio file or something, and if the IO device, some other IO device is requesting the CPU just to arbiter, be as a moderator, it's a total waste of time for the CPU. So in that case, what the CPU does is, what method was started is this direct memory access. So this one. So in that case, what happens is the IO device will directly just instead of doing all these ISR accesses 10 times and all those things, it will just um, give a request to the CPU. Okay, I want it will raise an interrupt. Once it will raise an interrupt, and in that interrupt itself, what will be there is, it will tell I want 100 bytes from this location, say A1. So there would be a limit of to how many bytes it can access at once. It can request. Say the cap is 50 bytes, or it can be 100 bytes also. Usually like a block size, page size, something like that. So based on that limit, it can request directly, okay, I want 100 bytes starting from this A1 location. The CPU, what will it will do, it will handle that, it will just handle it once, it will handle that interrupt, and it will give it will just give back the control to the DMA thing, it can directly access the DMA also, so it will give back the control to the DMA. So this DMA is a controller, it's a logic present outside the chip, and this DMA, what it will do is to transfer all these 100 bytes directly from the memory to the IO device without asking the CPU each time. And once this 100 bytes of data is transferred from the memory main memory to the IO device, the DMA controller will raise an interrupt stating that raise an interrupt to the CPU stating that this request of 100 bytes is over. So this is the logic of DMA access. So instead of interrupting the CPU for every 10 bytes of access, using this DMA controller, it's like an extra piece of chip that is being present outside that is just programmed to do this direct memory access. And the CPU just offloads the task of giving access to the memory to this DMA controller. This DMA controller will just do this copying and copying from main memory to IO device. Those things the DMA controller will do. And the CPU is saved from doing this repeated job, and it can just continue executing the application. And once this 100 bytes is over, it will raise the interrupt. The CPU will then check whether it's over, and if it's over, then it will just erase this task from the queue, and it will just continue again with executing the application. So all these interrupt cycles, the hundreds of cycles in used to save and restore back the registers, all those things are saved by using this DMA controller. So any doubts in this logic DMA controller? If not, then just move to the last question. Select the incorrect statement out of the following. Option A, on-chip communication is faster in multi-core system than multiple chips with single core. Option B, multi-core system is more efficient than multiple chips with single core. Option C, all multi-core systems are multi-processor systems. Option D, all multi-processor systems are multi-core systems. Any guess which one is the correct option? Option okay, option D is incorrect according to Mohit. Let's see. So let's see the first one. On-chip communication is faster in multi-core than multiple chips with single core. Yes. Anyone knows the reason why option A is correct? Sorry, the statement is correct. Multi-core system is faster because you don't have to cross your chip and use some external bus to interface. So say this is processor 1, this is processor 2, and this is a bus. So this is on chip and this is another chip. So to communicate between these two processors or these two chips, there is an external bus, and once this external bus comes into picture, there will be lots of delay because the same bus, other hardware devices attached to the system like the USB device or the main memory, all these things would be using this bus only, and there will be congestion. Only one chip or main memory or those things can be using the bus at a time, or there will be a limitation of how many chips or how many devices can be using the bus at the same time. So once this goes off the chip, this bus is off the chip, there is a delay. So that's the reason why multi-core system, that is you are having the same chip. This is this is the same chip, but this will be like one core. So this P1 as such, this will be like core 1, this will be core 2. So when they tell like quad core or something, so it will be like, okay, so 4 cores might be in a single chip, or it can very well be like two chips are there in one, two cores are there in one chip, and again there will be like C3 and C4 in another chip. So this also can be a design. So it depends on what they tell us like quad core design or something. Quad core is usually like 4 cores in a chip, I guess. So that's the thing. So multi-core system is usually faster because in a single chip itself you will have multiple cores. All of them would be mostly the same core, or you can slightly have different variations also. And option B is multi-core system is more efficient than multiple chips with the single core. Yes, it's same as option A. So both these statements are correct. So it's not these two. And option C is all multi-core systems are multi-processor systems. Yes. The reason being this cores as such, there are actually a processor in its own. It has its own ALU, the arithmetic logic unit. It will have its own registers and all those things. And say you have a given say Fibonacci program or something, can either be run on executed on the core 1, or it can be executed on core 2. It does not make any difference. And these are usually multi-processor systems only because notion is same. The only thing is they are present on chip itself. So this is also a correct statement. And we come to the last statement, all multiprocessor systems are multi-core systems. So this, as mentioned in the, as some of you had mentioned, this is an incorrect statement. The reason being multiprocessor systems does not specify whether all the cores have to be present in a single chip or it can be present in 2 or 3 chips. So this statement is wrong. All multiprocessor systems are multi-core systems. So the correct answer is option D, which is the incorrect statement. Okay. This brings to the list of questions that were asked, the end of list of questions that were asked in the previous offering of the same NPTEL course, operating systems course last year. Any doubts you have till now? Yeah, that's the end. So any doubts you have till now, whether so the assumption is we have gone through these 10 questions, and you have your assignment 1 released, and those questions would be similar to these in thinking. The way of thinking, it will be based on the week 1 lectures. So try solving those questions and do submit it before the deadline. The questions are pretty easy only. And yes, yes, that's it. And if you have any, so this these type of sessions would be um, given by me in the coming weeks also. So this is a 12-week course. So for all the 12 weeks till the last week, I would be giving these live sessions Friday 6 to 7 p.m. There will be other similar live sessions also. So in these live sessions, we would be the same agenda. We would be discussing the set of questions, and I'd be clarifying your doubts. So first week is be relatively easy because it's just like introduction and intro and the types of operating system, the DMA access, and those terms are all introduced to you. But in the coming weeks, you would be introduced to terms such as like process management and virtual memory, and afterwards paging, scheduling, file systems. So these things all would be introduced in the coming weeks. So these all these concepts put together only brings the operating system alive, and these are the features that the operating system offers you, process management and all these things. So in the coming weeks, it would be more in depth as in the questions, and also it won't be as simple. So it would be good if you attend the live sessions and clarify your doubts. Yes, that's it from my side. Hope you found this session useful. Um, If you have any other questions which occur to you later also, feel free to post in the discussion forum. I will be available in the discussion forum. You can just include the subject like PMRF live session or something and post your questions so that I can come and answer those queries as soon as possible, as fast as possible. So hope you enjoyed this session and hope you got clarity on what the course would look like and all those things. Anyone has any other doubts or any feedback? Whether yeah, yes, Mohan. Yes. Okay. Okay. So the firmware is something is usually different to an operating system. Let me yeah. So one is the middleware. So let me start with middleware. So middleware is something which is so just yeah, there's no like exact definition as such for these middleware. If you it's the so say you are having an let me make use of this Android OS. So if you know Android OS, if you just used it, uh, what happens is that in the any application running on the Android OS, right, it will be making use of a key value database, something like some database to store and retrieve information and all these things. Say your contacts would be stored in a database, your any other files, everything would be stored in a database thing like a file system, like it will be stored in a database. So multiple applications, the Android applications would be making use of this database, and this database as such is not running as part of your Android OS, OS mode. It most of the database that logic be running within the user mode itself, and this DB as such, this database logic would be servicing the requests put forward by the applications A1 and A2 like that. So in that case, you tell these services such as database, these things as middleware. So it's not as part of the operating system. It's not like just like an normal application. It has some specific use and it is servicing the request by other applications also. So that's what the term generally middleware is about. And second term that you asked is about firmware. So firmware is nothing but just so it's similar to like software as in this where is being used, and the term why it is firm is like it's non-volatile. You can think it like that. It's firm. It does not get erased or something. So this firmware is something it is usually in your hardware. This firmware would be hardware as in your sorry eraser, yeah. So so firmware as in this is your disk or say read only memory. So in this thing your firmware, yeah, so it can be writable also. This can be like secondly disk storage or something like that also. So the firmware would usually be stored in this. So this firmware is something which would be say the bootstrap program which you would have studied in the week 1 lecture, that is which gets the um, operating system from the disk into the main memory, those things. So all those things would, that logic would be present in the firmware. So the firmware is something which should not be erased. So on power owning switching on the device, this firmware would be executed. So it's like a set of instructions which will mostly be executed always when it's being switched on like that, and this will then boot the OS or whatever the application is. say you even your USB device will also have some firmware attached to it. So whenever you plug in your USB device to a system, some operations say like you have to refresh all the memory contents once. You have to check whether any that so in a say if you are in a USB device there would be this storage cells like the underlying technology. Those storage cells, those things, whether anything has been corrupted or not, whether anything has been damaged. So those things all would be present as part of the firmware, or the firmware would be small in size and that logic would be executed by the firmware. It would call those functions. So it is firm as in it's non-volatile and it's present on the device always. And this firmware is, you should not confuse it with the operating system. The operating system is something else. It's a layer above the firmware. This firmware usually calls the transfers control to the operating system, like that. So hope you understood the terms middleware and firmware. And the key thing with these things, right, Mohit, in your operating systems week 1 lectures, you would have come across variety of terms. You would have come across batch operating systems, multi-user, multi-programming, so many things you would have come. So the thing is like, yeah, these terms are important, but try to understand the meaning of these terms. So multi-user, multi-programming, it's the functionality is same, but in multi-user, it's like multiple users are being trying to execute, and in that case, user, whether we are mentioning it to like an individual person as such, it's being using the system, or the user as in like an individual application that is being using the OS. So in that case, it's like multi-programming if it's an application. So these are all like subtle terms, and just for a newbie who gets started into operating systems, for them these terms were all there and to make it more for better clarity. But once you understand, right, you usually don't use these terms frequently when you try digging deep into the operating system or something. These terms don't make much thing. It's just a feature of the operating system, whether it supports multiple applications at the same time, whether it supports multiple users. So it's so those features are just being given terms over here. So just understand the concept, that is more than enough for these initial things. And from week 2 onwards, it would become more detailed as in the internals of the operating system, how each of these features are being implemented in the operating system. Okay. So, yeah, any more doubts? Uh, any feedback? Should I change the way of teaching? Whether there was any noise on my side or something like that, or can continue the same type of sessions in the coming weeks also. Okay, I'll just assume everything went normal from my side then. Okay, then in that case, let's stop the session if there are no more doubts. You are free to post any doubts in the question, the discussion forum. I will be available. Just mention the subject alone as a PMRF live session, uh, Friday 6 to 7 p.m. like that. So there are actually like two of other TAs also. So yeah, this live session will be every week. So you can join these live sessions and clarify your queries. And we'll be discussing in a similar way other questions for every week based on the assignments that are being released for you the next week. Okay, then thank you so much for attending the live session. Hope you all found it useful. And in that case, see you all next week, same time, same meeting link. Okay, thank you so much. Thank you, Mohit. Thank you.